This last section looks at applications of exponential functions and logarithms. Where in real life do logarithmic equations and exponential equations come up? And there's a number of places that they come up, and we're going to be doing some examples with those. Here's just a list. Population growth. Population growth normally grows exponentially. So you might have heard of that before, and so populations can be modeled with exponential equations. The first questions we're going to look at are some compound interest formulas. And we've talked about compound interest a little already, how you make interest on interest, and we have the formula and we saw it already. That was when we could only solve things with our graphing calculator. Now we're going to be able to solve these equations using logarithms as well. Decibels. So for sound, decibels goes up exponentially. Going from 110 decibels to 120 decibels is a huge increase. Same thing with the Richter scale and earthquakes. An earthquake of 7 compared to an earthquake of 8. The 8 is 10 times bigger than the 7. So every time you go up 1 on a Richter scale, you're going up 10 times. So a 6 compared to an 8 is 100 times more powerful. Or I mean the 8 compared to a 6 is 100 times more powerful. If you're taking chemistry, your pH scale is also an exponential growth scale. We also have exponential decay. Some things, some radioactive materials have half-lives. Drugs in your body have half-lives. For example, when you take Tylenol for a headache and you're reading the back of the bottle, it's telling you stuff. Don't take 2 pills every 4 hours. It's probably because the half-life of that pill is 4 hours. And those instructions are on there so that you don't cause your body to have problems, so you don't overdose. So for example, if you can take 1,000 milligrams every 4 hours, that would mean after 4 hours your body will have used up half of that 1,000. There might only be 500 milligrams still in your body. So when you take 2 more pills, you now have 1,500 milligrams in your body. 4 hours later, your headache's not gone, you have 750. You take 2 more pills, now you're at 1,750. But in that process, you will never get past 2,000 milligrams. Because if you take 2,000 milligrams, 4 hours later, you'll be down to 1,000, and taking 2 more pills will put you back at 2,000, but you can never get past that. So they know what limits your body can handle. They also know that it's not good to hit that highest limit right off the right away, because that might be bad for your system. So those kind of things are studied, and mathematics is used to figure them out. So we've already seen this formula. Again, all of the formulas that you get will be given to you in the question. So if you have a question that involves a formula, a word problem that needs a formula, it will be given to you with all of the things explained. But we do need to work with some of them to get a handle on what they are. So these first 2 or 3 questions are relatively straightforward. So I'm going to get you to try all 3 of them. Plug things, read the formula, plug things into the formula as best as you can, and solve for what they're asking for. I'll put up the answers in a second. So do a quick check. Did you plug everything into the formula correctly? Compounded monthly means that n is 12. The percentage as a decimal is 0.0225. You can type this all into your calculator all at once. Push enter. And $626.03. Give you another minute or 2 and we'll go over the next one. All right, our second one. Compounded semi-annually means twice a year. Again, make sure that your rate is as a decimal. And what I have in the red there is if you have the older calculator, okay, and this shows up with a little hat button, and you put 2 times 5, that needs to be put in brackets. Otherwise, that exponent will just do the exponent of 2. If you have the newer calculator where your exponent is actually smaller, then you don't have to worry about that. So if these are numbers, if you're not getting these numbers, it's sometimes a problem with how you put it into your calculator. So not only do we need to know how to put our numbers into the formula correctly, we also need to know how our calculator operates so that we can get our calculator to give us the answer that we want. Now on this third one, calculate the time. This is the first time when we plug in everything that we know that what we're trying to solve for is an exponent. So it's compounded monthly, so n is 12. The rate is 7%, so I write that as a decimal, 0.07. And now I'm solving for t in an exponent. Solving in an exponent, you have two methods that you could use to solve for that. You can use logarithms, or you can get the bases the same. The base of this exponent is not a pretty number. Okay? So you know right away, I don't know my powers of 1 plus 0.07 divided by 12 very well. So you know that this will be a calculator question. Now, as a first step, it makes your life easier if you can simplify it at all. So notice here I divided both sides by 30. Then I get 2 equals 1 plus 0.07. And I knew that this had to be 30 and 60 because my investment doubled. So if it was originally 30, it becomes 60. And the really cool thing about this is, well, this mathematically is really fascinating, is if you started with $300, to double, it would be $600. But if you divided both sides, you would still get this equation, 2 equals. If you started with $1 million, doubled it would be $2 million. But if I divided both sides by 1 million, I would get 2. Okay? Now that's interesting because from this equation, if you go to solve, if you take the log of both sides, now that exponent is to the entire thing, so you can bring that 12t out in front. You want to solve for t, so I can divide by 12, and I can divide by this log, 1 plus 0.07 divided by 12. They're just not pretty looking numbers, but they're still numbers. I type this into my calculator, and I find out that it takes about 10 years. So we used our logarithms, and it will take about 10 years for your $30 investment to double to $60. Now what's crazy about that is that means if you had invested $1 million, it would take 10 years to double. If you invested a nickel, in 10 years you'd have 10 cents. Right? Not nearly as exciting. But it shows the power of interest rates. It takes the same amount of time to double no matter what your principal is. So if you have a lot of money, you will have more money. And if you don't have very much, you don't, like, doubling doesn't make very much. So if you can convince someone to just like, hey, if you're not using it right now, if you could just borrow your $1 billion for the next 10 years, I'll give it back. You could double it, give them back their billion, and you'd have $1 billion in 10 years. That would be really cool. Unfortunately, it's very hard to find those people that will just give you $1 billion. That also is very hard to do right now, 7%. It used to be that you could get interest rates like that, but now those interest rates are harder to find. Now I'm going to teach you just something off to the side that's interesting. It's called, sometimes it's called the rule of 70, sometimes it's called the rule of 72. It just matters which math is easier for you to figure out. The rule of 70 or the rule of 72 works basically like this. $70 divided by I is your interest rate. So in this case, in the example we just did, our interest rate was 7%. So I look at the rule and I either use 70 or 72, whichever one's easier, divide by 7. 70 is divided by 7 quite easily. What is 70 divided by 7? 10. And that gives you a pretty good approximation of how long it's going to take for it to double. Notice it took us 9.93 years. 10 is a pretty good approximation. So if you got an interest rate of 6%, well, 72 divided by 6 is 12. it would take about 12 years for your investment to double. If you got 10% interest rate, I would use this one, 70 divided by 10 is 7, it would take approximately 7 years for it to double.